Hi everybody, I'm Dr. Lindsay Pease, and I am the Nutrient and Water Management Specialist at the Northwest Research and Outreach Center in Crookston, Minnesota. And for today's video, I am going to be talking a little bit about cover crops in cold climates and talking through some of the reasons why I think that this might be a concern from an environmental perspective, really specifically for the Red River Basin region that I primarily work in, but also it's a potential throughout the state of Minnesota. And since we've got a lot of freshwater lakes, phosphorus issues can be really detrimental to aquatic habitat in any freshwater system, any freshwater lake. So that's what my focus of this video is going to be. So let's get right into it.
When we talk about phosphorus and cover crops in the Red River Valley, really what I am thinking about is how do we manage this phosphorus relief from cover crops? We know, and from an experiment that was done by Dr. Al Sims, which I will talk about in a minute, we know that frozen cover crop residue releases phosphorus. And because we know that it releases phosphorus, then we need to start thinking about how we manage for that phosphorus release and how we can incorporate that in our soil management plan and our cover crop management plan. And really the two techniques I'm going to talk about today are preventing phosphorus buildup in the soil and reducing the potential for surface runoff in the spring. Now, when we talk about phosphorus release from cover crops, this is a potential negative trade-off that we see with cover crops, but that is not to say that there aren't many benefits that outweigh this potential phosphorus release. Cover crops have all the benefits you see on the screen, from providing soil cover to being a subsoiler, scavenging nutrients, and providing some nitrogen fixation. They also can have beneficial effects on habitat, providing habitat for pollinators and bees, and may also have forage value if you have livestock that can graze on the cover crops during the non-growing season. The other thing that we know about cover crops is they really need a management strategy. They're not something that you just decide one day, I'm going to go seed cover crops, and you go right out and you throw a handful of seeds out there and they grow. They really need a lot more planning and strategy to be successful, especially in our cold climate and with our short growing season. And one of the questions that we don't really talk about as much as some of these other questions is really that question of fertility management. So my fertility management plays into this is, you don't need to fertilize the cover crops themselves, but in northern Minnesota, it's really common, in Minnesota in general, it's really common to apply fertilizer in the fall. If you have kind of a warm season after harvest, this past year, 2020, was a really good example. There was a string of good weather in October, dry, and most people got out and got their fertilizer applied in the fall. But if you're also thinking about that is your window for seeding a cover crop, how does that play in? And is your cover crop sort of going to kind of be work with that strategy, or would you be better off waiting until the spring after the cover crop kind of dies off a little bit to apply your fertilizer? These are all questions that we don't really have great answers to, and we don't think about as much, and is maybe sometimes considered a secondary question to these other really practical cover crop ways you get cover crops established. So in order to talk about how we know and what we've seen as far as cover crops releasing phosphorus, I'm basing this off an experiment that was done by Dr. Albert Sims. And until recently, Dr. Sims was the Director of Operations at the Northwest Research and Outreach Center. And now he has begun phased retirement. He's still a professor in the Department of Soil, Water, and Climate, but that's the reason why I'm talking to you about this data today, as opposed to him, because I'm sort of taking this on and thinking through this analysis and really thinking about how this is going to apply in our cover crop management strategy. And I'll also say, Dr. Anna Cates, who has another video that you can watch for this meeting, you can go check that out. It's on a totally different topic, but she's also helping me kind of think through some of the management implications of this data. And so there are so back to the experiment, there were 3 species of cover crops that were seeded in field plots, and they planted these after they did a fall fertilizer application for the next year. So again, not fertilizing the cover crops themselves, but fertilizing for the cash crop the next season. And Albert wanted to test 3 different application rates of P2O5, 0 pounds per acre, 75, and 150, and wanted to see how that may or may not affect the release of phosphorus from cover crop residue. So these cover crop species were planted in the field and let grow for a little bit, and then the vegetation was sampled in the field and frozen in the lab. And then once the vegetation was frozen and in the lab, they were put into mesh bags and submerged in distilled water. So that's what you see in the jars on this slide. And in these 2 images, there's some bags with the cover crop residue kind of stuck inside, and there was a known amount of water added to all these jars. And after 24 hours, after 1 day, all the water was drained out, and then the concentration of water was measured. The concentration of phosphorus in the water was measured, and this was repeated every day, every 24 hours over 4 days. So this slide shows the results of this experiment, and it's a little bit of a busy slide, and the colors in this graph as it defaulted out were not that great, so I'm just going to talk you through a few things on this slide. First of all, on this graph, the top line is always going to be cereal rye, the line in the middle is forage radish, and the bottom line is buckwheat. And on the y-axis here we have SRP, that's our dissolved phosphorus concentration, and below that is total phosphorus concentration. Along the top we have those 3 different P2O5 rates that were applied that the cover crops were seeded into, from 0 to 150. And at the bottom, we see the hours of the residue the hours the residue was submerged, or kind of, what day it was in that cycle of submerging the residue, letting it wait, and then draining the water out. And then that process again repeated 4 times, so 24 hours to 96 hours. And what we see on this graph is, well, first of all, the cereal rye seem to have a slightly higher phosphorus release than the other 2, but those differences between the cover crop species really started to go away once you added higher phosphorus rates. So I think one of the big conclusions here is that if you've applied more phosphorus onto the soil and then plant your cover crops, you are going to get potentially more release of phosphorus from that residue than if you hadn't applied anything. And I think that makes sense, because if you think about it, you apply the fertilizer, it's for the cash crop, but the cover crop is going to take it up as well. And that's when we start thinking about, okay, well, the cover crop's taken it up, it's scavenged it, but is it actually releasing at a time that's useful? And those are some of the questions that we have left to answer. The other thing I want to point out on this graph is that obviously that first submergence event, the first 24 hours is when the most phosphorus was released by this residue. But over time, there still is quite a lot of phosphorus released even after the fourth submergence event. And if you think about it, this was clean water that was submerging these cover crops each time. So this is really the most came out in the first 24 hours, but over time it kept releasing phosphorus. So it wasn't just like a one-time wash. It was a little bit, or it was a lot at first, and then a little less, a little less, a little less. And to kind of put some context to the values you're seeing, those concentration numbers, I do have a couple dashed lines on our graph, and at what almost looks like 0 parts per million for SRP for our dissolved P, that's actually 0.05 parts per million. And that's the level that is known to be, as a concentration level, potentially harmful to aquatic life. So, in a small quantity, in being in a concentration that's in that jar, if you were to put a fish in there, it would not be very happy because algae could grow, and the algae would take up the oxygen that's the fish needs. So that's just kind of where that number comes from. But at the same time, I'll also say that a lot of things happen to that water, even though it's maybe high in that jar, a lot of extra water is entering the system at the same time. So this is not necessarily the concentration you would get at the end of a drain tile or in a ditch next to it, but it is a starting point, and it's going to dilute downstream. But we still don't want to really be adding concentrated phosphorus to the stream if we can help it, especially when that phosphorus can be really useful for your next year's crop. The other line on the bottom is the recommended concentration of phosphorus in the Red River at the US-Canada border. And again, you can see how our concentrations are highly concentrated phosphorus that's released from the cover crop residue is above that limit. So we're really counting on the water and the rest of the system to be able to dilute that so that we're not over concentration at the border. So even though there's a lot that happens to the water in between the time it would be, released from the cover crop, and the phosphorus would be released from the cover crops and make it into the field, make it into the stream. These are just good benchmarks to have in mind, and really is a reason why we need to think about this, and we can't just say, well, this isn't a problem. So I've talked a lot about, okay, we know that the phosphorus is being released by the residue, so how do we keep it in the field? Well, when we're managing for phosphorus released from cover crops, you really want to think of this as managing not to prevent the release from happening in the first place, but really to think about how you can keep it in the soil. And kind of the two things I want everybody to think about and to remember are, first, you want to tie it up in the fall. When it's released, you need to have binding sites for that phosphorus. So once it's released, it can bind to the soil and stay there through the winter. And then second, in the spring, once everything thaws and melts out, you need to be able to keep that soil and water in place in the spring and in the field, so that any phosphorus that's tied up on the ground surface stays there. So tying it up in the fall, I just have a couple images to help everybody kind of visualize this process that's happening in the fall. On the left-hand side of the screen is a newly established young cover crop plot on October 18th, freshly seeded after wheat harvest. And it was a really wet year, so you can see some of the wet soils and ponds in the background. But it also was a year that had a fairly early first freeze, And that freeze happened kind of in between the time when the first picture was taken on the left and the second picture on the right. And the picture on the right, you can really see how that residue just really shriveled up, and the cold and the frost really did sap that residue. It didn't kill it entirely, but definitely this would have been a time when we could have seen some phosphorus release from that residue. And so we want to make sure that on October 30th, when that freeze happens, that there's space in the soil for that released phosphorus to bind. So something that I think you have heard, me or Albert Sims talk about a lot is really this build and maintain versus the sufficiency approach to phosphorus management. And phosphorus buildup, once you have that very high soil test phosphorus level, not only is it not beneficial from a yield perspective, it also means that you could be running out of binding sites in your soil. So when the phosphorus is released from that cover crop residue, all of those sites are already tied up. All that calcium in the soil, if you have really high soil test phosphorus, and you add more phosphorus on top of that, there's no place for it to bind, and we also know that that's really has a high likelihood of then running off, getting carried away in the first rainstorm, the first heavy rain that happens. So you want to make sure you have those binding sites available. And I'm not going to talk very much about this study because I think you guys have heard about it a lot from different people, but just know that the build and maintain does not out yield the sufficiency approach. So just fertilizing every year based on your soil test is definitely the better strategy to go from both a yield and kind of economics perspective, and also in terms of managing to keep that phosphorus in your field. It's like a win-win. Okay, so you've tied up the phosphorus in the fall, and now what you need to do is try to keep that soil and water in place in the spring. So to explain that a little bit better, I just have a couple of quick animations that I made up in PowerPoint to help explain what I mean. And so first we have an unfrozen soil profile. You have the blue here is the sky, the white bar across the kind of top in the middle is snow, and the brown is the soil profile. So when that snow melts in the spring, what normally happens if there's no barrier to that snow, it's going to absorb down, move downward freely into the soil profile. But what happens often in Northwest Minnesota and in the Red River Basin is that we actually, as the snow is melting in the spring, we still have a frozen layer sandwiched in the soil profile. And I've seen this on some of the temperature graphs, and it's a little bit of an odd phenomena because the soil is, warmer, really deep, and at the surface, at your top, 4 or 5 inches, it could be thawed. But there's still this kind of insulated frozen layer sandwiched in between. And so here we have our snow again, and then the kind of purple frozen bar. And when that snow melts, there's not enough space for it to move downward. It's sort of blocked by the frozen soil profile, and it does eventually thaw that out. But in the meantime, what happens is that the amount of water that can't infiltrate is actually just going to stay on the surface, and the top few inches of the soil profile is going to be really saturated and disconnected from deeper layers. And so anything that's left and that's freely available, whether that's soil, whether that's phosphorus, is going to be picked up by the water and potentially carried away if it moves off site before it has a chance to infiltrate. So then what we want to do in that scenario is we really want to minimize runoff and erosion. And sometimes this is hard because if you're really, right next in a flood prone area, there's probably not a lot you can do to prevent some of the spring flooding, but you can manage at least a little bit and kind of give your soil its best chance at staying put. And in this way, cover crops actually can be part of the solution. If you have living roots in the soil, that's kind of like the buckwheat again that you see on the left-hand side. Having really fibrous root system can help hold the soil in place. So with that, I will just kind of wrap up here. The phosphorus released by cover crop residue is a potential concern after the first killing frost and during snow melt. It's released from the crop during those frost events, and it's going to stick around. And in snow melt, if the snow and the water is moving off the field quickly, it really has a high potential to carry that phosphorus with it. So preventing phosphorus buildup in the soil and preventing surface runoff can really minimize the risk of P release to the environment that's caused, or that could be caused by the cover crops. So with that, I'll just throw out a couple of acknowledgments. Again, the experiment was designed and the preliminary data analysis was done by Dr. Al Sims, and Dr. Anna Cates, the University of Minnesota soil health specialist, helped a lot in the data analysis and interpretation and kind of turning this into useful products, for all of you. So there's more to come on this, but thought I would give you all it's a good topic for today's conference, especially with the other videos that you definitely should check out on phosphorus loss in other regions.
So thanks everybody for watching, and hope you enjoyed today's video. And since we're doing this in a virtual format and you can sort of pick and choose or jump around in what videos you watch, I'm also going to give a quick plug for a couple other videos that are available and that I think might pair really nicely with mine. So go check out Maren McRae's video on cover crops in Ontario and Nathan Nelson's video on cover crops in Kansas to really get that other perspective of the landscape effects of cover crop management on this question of phosphorus loss. I think it's a really interesting question, and while it may or may not outweigh the actual benefits, and it probably doesn't outweigh the benefits of actually doing cover crops, I think it's still really good to keep in mind, and you always want to think about those potential trade-offs of what you're doing. And then think about ways that you can minimize that risk. With that, I will sign off, and please let me know if you have any questions, and hope to chat with you all soon. Thanks.